Then start, sir. Okay. Good morning to all. On behalf of Chip-in Center, we welcome you to the today's session. IBM is conducting a series of online technical sessions covering open power ISA, microwatt microarchitecture, and its build using open source EDA tools for all the academic institutions and startups. We kindly request all academic institutes and startups to take this opportunity to gain insights into microwatt microprocessor microarchitecture. We are privileged to have Dr. Paul Mackerras from IBM with us today. Dr. Mackerras will be delivering a technical session on the microwatt microprocessor microarchitecture, a topic of great relevance and interest to all the participants. With his extensive expertise and deep understanding of microprocessor design, Dr. Mackerras will provide us with valuable insights into the architecture, features, and innovations of microwatt. This session promises to be highly informative and enriching for everyone involved. It is my great pleasure to introduce our distinguished speaker of the day. Dr. Paul Mackerras is a retired IBM senior technical staff member in the IBM Linux Technology Center. He holds a PhD from the Australian National University. He has contributed to the Linux kernel for more than 20 years, particularly in the area of support for the power architecture. He also served as the architecture maintainer for the PowerPC architecture for 7 years. His most recent contributions improved the Linux kernel virtual machine code supporting IBM power processors. Thank you very much, Dr. Mackerras, for graciously accepting our invitation and delivering this enlightening lecture to all the participants. It is an honor to have you with us today. On behalf of CDAC Bangalore, I warmly welcome you and express our sincere appreciation for your time and valuable insights. Today's session will cover a general overview of microwatt and gives an introduction to the microarchitecture of the microwatt processor, including variants that support the integer and floating point subsets of the architecture. Thank you all the participants for joining the session. Once again, we welcome you all for this session. And now I, on behalf of Chip-in Center, request Dr. Mackerras to take over the session. Thank you, sir.
Great, thanks. Thanks for the introduction. Just remind me how much time I've got. Have I got 45 minutes or is it 45 minutes or is it an hour?
Yes, sir, around 45 minutes.
45 minutes, great, thanks. Okay, can everyone see my screen okay?
Yeah, it is visible, sir.
Yeah, I should explain that I'm actually not still working for IBM because I retired, as you said in the introduction. So I'm from IBM in the sort of longer term sense, but not immediately. Yeah. So, okay, so what is microwatt? Back in August 2019, IBM and the Open Power Foundation made the Power ISA open, meaning that anyone could implement a complying implementation without paying royalties. And as a demonstration and proof of concept to show that you could actually do something kind of useful with this, one of our engineers, Anton Blanchard, who's a distinguished engineer, was at that point a distinguished engineer with IBM, decided to do a very simple core that would implement the power instruction set and show that it was possible to do, in a fairly compact fashion. So that's what he did, and he released that, and then several of us have been working on it since then. In the last couple of years, it's mostly been just myself who has been working on microwatt. It's deliberately being kept relatively simple. I mean, it's not really simple, but it's relatively simple, particularly compared to the commercial cores that IBM does implementing the Power ISA. Something like a Power 10 is a very large scale superscalar implementation with billions of transistors on each chip, that kind of thing. This is designed to be simple enough that people can read the code and understand what's going on. It's designed not to be more than one person could reasonably get their head around, and it's designed for implementation on smaller FPGAs of the sort that you can buy. I've got a couple of FPGA boards here One has got a Xilinx Arctic 7 FPGA on it, and the other's got a Lattice ECP5, and they both cost a few $100 US, and so they're quite within the reach of many people to just buy one for themselves and try things out on it. The name MicroWatt is actually a kind of pun. When Anton was thinking about a name for the project, he thought, well, this is power. Now it's only a very small amount of power because, you know, it's just a very simple implementation of the ISA. What's a name for a very small amount of power? I know, let's call it a microwatt. So that's why he called it MicroWatt, which is kind of cool, but it does make it hard to do a Google search, because if you do a Google search for MicroWatt, you find lots and lots of other things. But it's on GitHub. If you go to GitHub, Anton Blanchard /MicroWatt, you'll find it there. So all the code is there. It's open source. Anyone can just clone the repository and have a look, and they can contribute. So people can use the normal GitHub process to make a fork of the repository and put their own stuff in it, and then send a pull request. And maintainers, i.e. me, will look at the pull request and decide what to do about it. Another thing that we get with GitHub is a degree of automated testing, in that GitHub has got machinery to run a series of tests on each pull request before it gets incorporated. So in that way, we've been able to do a moderate amount of low-level checking that instructions basically work, and you haven't completely broken the add instruction, for instance, with your pull request. Now, the MicroWatt currently uses the Wishbone memory interface. This is a memory bus standard that's often used in FPGAs, and it's basically just got address and data lines and some control signals, and it's relatively simple. For peripherals, since we wanted to focus on the core, for peripherals to make a usable system, we've mostly taken in code from the Litex project. So, for example, there's a dynamic RAM controller and an Ethernet interface and a SD card interface that we use that come from Litex. Now, MicroWatt aims to be a compliant power instruction set architecture version 3.1c implementation. One of the things we got with version 3.1 is these prefixed instructions. These are quite new. They only came in terms of IBM servers. They only came in with Power 10, and I'll explain a bit more about them later. It implements, I should have written this, it implements the scalar fixed point set subset and the scalar fixed and floating point subsets of the Power ISA. I think Peter Hofste, in a previous talk in this conference, talked about the Power ISA generally and the compliance levels. So the two lower ones are the SFS, that's the integer scalar stuff, and the SFFS, which is integer and floating point scalar. So we've implemented about 300 instructions in MicroWatt. That's the number of instructions in those subsets. To implement the vector instructions in the Power ISA would be another 700 instructions. So it's I think over 1,000 instructions when you add the vector, the VSX and the VMX instructions. So we don't implement the vector because it would just make it way too big for the FPGAs that we've got, and it would make it very, very complex. However, we do have enough to run Linux. The support for Linux is in the upstream kernel. It's its own platform called MicroWatt. It doesn't require vector stuff, and you can boot on one of these little FPGAs, these boards that have got, let's say, 256 or 512 megabytes of memory, and you need some kind of like SD card interface for your disk, and then if you've got Ethernet, that's good, and you can use it as a little embedded Linux microprocessor. So on the next slide, I've got a picture here that shows the structure of the pipeline. So it's a fairly simple in-order pipeline. We've got fetch and decode at the start. I'll talk about each of those stages in more detail in a minute. And then we've got these 3 execute pipelines, but things always complete in order. They're always issued in order and complete in order. So it's an in-order machine. It doesn't have any out of order superscalar type capability. And the reason for that, of course, is just simplicity and keeping it small. It has, I've shown the load store unit, which handles the load and store instructions and those kind of things. The execute pipeline, which has got 2 stages. Load store has 2 stages as well. And then the floating point, if I get time, I'll talk about that. And that isn't pipelined. It's a fairly simple state machine of its own that takes one instruction at a time and works on it. And then we have the memory management unit, data cache, instruction cache, and over on the right we have the performance monitor unit, which counts events of various kinds. Now, when you put that within a complete system, you have the core over here on the right, and that has these wishbone interconnects that go to an arbiter that arbitrates between the accesses from the data cache, the instruction cache, and actually DMA accesses as well. Then there's an address decoder, and we've got a level 2 cache dynamic RAM interface on the left, so we can access our dynamic RAM. Some block RAM used for initialization. That's only a relatively small amount, like 16 or 32 kbytes. And then an I/O decoder that distributes the accesses to the various different peripherals that we have there, a system controller, SPI flash for some non-volatile storage, serial interface, an interrupt controller, the XICS, Ethernet, SD card, and if you have other things, they hang off there as well. One thing that we have is the ability here on the left, we've got the ability to connect to the system via JTAG from a host machine, and from that to access memory, and also to start and stop the core and single step it and that kind of thing. So you can debug the system even when it's working so poorly that it can't run anything. You can still get in and see what the contents of registers are, what the contents of memory are, what the PC is, and that kind of thing. Okay, so starting at the top of the pipeline there, we have fetch 1. That generates a sequence of addresses for instructions, and it generates both an effective, that's a virtual address, and the corresponding real address, which most people would call a physical address. So effective and real are IBM terminology that correspond to virtual and physical in most of the rest of the industry, but IBM has its own terminology. So fetch 1 is doing the address translation for the instruction accesses. Previously, we had that done in the iCache, but for various reasons, it turned out to be better to do that in fetch 1. So now that's what we do. So this address basically just starts at 0 or 100 hex when you reset the machine, and then just increments by 4 every cycle until you get a redirect. And a redirect is something from the execute unit that says we've executed a branch instruction, or we need to take an interrupt, or we've just executed a return from interrupt instruction. And then isync is another one that basically just, it doesn't cause a branch, but it just pauses fetching and flushes the pipeline and then continues execution. So it is very like a branch to the next instruction in terms of its effect. So those things cause a redirect. Decode 1 can actually cause a redirect for a predicted branch. If a branch is predicted taken, that can cause us to redirect. So we have the instruction TLB in here. We have a tiny 2-entry cache of that. And we also have an optional branch target cache where when we see that we've executed a branch instruction, a direct branch, in other words, one where you can work out simply from the instruction itself, you know, the bytes of the instruction, you can work out what the target address is. We store the address of the branch and the target address and whether we did actually take the branch or not. Then when we come up to that instruction address again in future, we can say, oh, last time we came to this address, it was a branch to that address and we took the branch. So let's redirect fetching over there. So that's what it does. So that means that for short loops, for loops of at least 3 instructions, we can get zero overhead branching. We don't get a bubble from the branch back to the beginning of the loop. Then we have the instruction cache. Its job is to read instructions from memory and cache them and supply them to the decode phases. One of the reasons that we went to using real addresses coming in from fetch 1 is that means that we can use the real address for indexing and tagging in the iCache, and that avoids aliasing problems that you can get if you have a virtually indexed cache where the set size is larger than the page size. You can end up with multiple copies of the same physical address in different locations in the cache because they've been used with different virtual addresses. But we avoid that by using the physical address for accessing the cache. Now, one of the things we do here is we do pre-decoding of instructions. So when instructions come in from memory, when we've got a cache miss and we're reading them from memory, we take the 32-bit form, which is, you know, the 32-bit instruction, and we look at the top 6 bits, which is the primary opcode, and the bottom 10 or 11 bits, which is an extended opcode, and we work out what instruction it is, and we then assign effectively a 9-bit, because I said that we implement about 300 instructions, so it's a fairly dense encoding from, you know, 0 to 320 or so, with a different index for each instruction, and that helps us with the decode, and I'll show you that in the next slide. So we take this top 6 bits and replace it by this 10-bit value. It's 10 bits because that ends up with 36 bits, and 36 bits is convenient for the block RAMs inside FPGAs. So that neatly fits into a block RAM that we then use for the iCache data storage. The other thing that the instruction cache does is that it's got a bus that lets it watch what is being written to memory. And if it sees a write to memory that corresponds with a cache line that it has currently resident, it invalidates that line. So that helps with when you're writing instructions to memory to make sure that you can then later execute them without getting stale data from the instruction cache. So then decode 1 and decode 2. Decode 1 has got this big table, a decode ROM, that's, I don't know, 80 or 100 bits wide and is indexed by this instruction index that I talked about before that ranges from about 0 to 320 or so. So that's a nice dense encoding for indexing into this instruction, this decode ROM. And then that gives a lot of control signals that control how operands are decoded, what function the ALU does, what result you select, and a bunch of other stuff. So there's, you know, quite a wide set of control signals there that then go down through the pipeline to control how the instruction is executed. Decode 1 also does static branch prediction for direct branches, and it computes register file addresses for the general purpose registers and the floating point registers. So we have up to 3 register operands. Power instructions can have up to 3, well, in some cases actually up to 4 register operands, but that's in the vector subset. I don't think there's any scalar instructions that have more than 3, but there are many that have 3. So we have a triple ported register file that holds both the general purpose registers, 32 64-bit general purpose registers, and 32-bit 32 64-bit floating point registers. So there's a total of 64 registers there by 64 bits. And we have 3 read ports and 1 write port, effectively. In an FPGA, what happens is you end up having 3 copies of it. So you have 3 sets of block RAM that are all accessed in parallel for the 3 read ports, and then writes right to all 3. You know, in an ASIC implementation, there might be another way to do it, but that's what we do in FPGAs. Now, decode 2 is probably more like an issue stage rather than decode. It's called decode 2 because that's what it was when Anton did the first version, and no one's changed the name. So it's about scheduling and dispatching instructions. It's the stage where we calculate instruction dependencies, because in a pipeline system, if you have dependencies between instructions, you've either got to stall the pipeline to account for the dependency, or use result forwarding. So an example is if you have, let's say, an add instruction that generates a result and puts it in register 4, and then the immediately following instruction is another add that wants to add R4 and something else and put it in, R5. And in that case, the second instruction depends on the first instruction, because the first instruction is producing a value that the second instruction needs. Now, in fact, in MicroWatt, because we've got a forwarding path from execute 1 to decode 2, we can actually do those back to back without a bubble between them. But let's say the first instruction was a divide instead of an add, and a divide is a long instruction that takes many cycles. So the second, the add following the second instruction has to be stalled until the divide is finished doing its stuff and eventually comes up with a result, which can then, be put into the add instruction as well as being written to R4. The other thing that decode 2 does is immediate operand selection and formatting. So on the basis of signals from the decode ROM, it can take bits from various different instruction fields or the address of the instruction and supply that as an operand. So at the output of decode 2, going into the following stages, which are the load store, the execute, and the floating point unit, at that point we have 3 64-bit values, which are the actual operand values to use, so that the following stages don't do any register access. They just take the operand values that they've been given and work on that. Now, I said previously that I would talk about prefixed instructions. So here's an example that shows how we handle them, because they're handled in decode 1. So at the top here, you see we have an example of an instruction, which is what we call a word instruction. That doesn't mean that it operates on a word, but that the instruction itself fits into a word, a 32-bit word. In the power architecture, word means 32 bits and double word means 64 bits, and half word means 16 bits, which is, if you've come from an Intel world, that's a bit different, but that's how we use it. So in a word instruction, in a load floating double instruction that I have here, this is load floating double word into floating register 2, and the address where to get by taking what's in GPR4 and adding 20 hexadecimal, 32 in other words. So that instruction fits into 32 bits, and it has a major opcode of 50. That's the major opcode for a primary opcode, I should say, for load floating double. That's 6 bits wide. And then we have a field for the destination register, which is floating register 2, and a field for this RB that we call it, which is, sorry, that's RA, which is, the index register, register 4, and then a immediate field here for the displacement. So this D field is 16 bits. And when we prefetch that from memory and put it in the instruction cache, we do the pre-decode, which says primary opcode 50 is a load floating double, which has instruction index 260. So we'll put 260 in this field, which is now 10 bits wide, and that's what gets put into the instruction cache and then supplied to decode 1. And so it's entry 260 in the decode ROM that gets looked up. Now, if you have a prefixed instruction, that actually consists of 2 words. So you have 2 32-bit words here. You have this first word, which has a primary opcode of 1, and then you have a second word, which is called the suffix. Now, this is a prefixed load floating point double word. Once again, the destination is floating point register 2, and we're using a displacement offset from register 4. So register 4 is our index register. But you see here that the displacement can now be much, much bigger than it could before. So this is part of the reason for having prefixed instructions, is that we can now put effectively the address of a variable in here. So we can address variables directly. I mean, previously with a 16-bit displacement field, we generally had to have another register pointing to the start of a data area or something like that, so that, you know, it was a little bit indirect to get to a variable in memory typically. Whereas with prefix instructions, that field is big enough that for most programs we can actually just have the address. And then if we put register 0 as the index register in the architecture, register 0 as the index register means don't use the contents of register 0, use the value 0. So if that was register 0, then we could just put the, you know, the absolute, well, the effective address of the variable that we want to access in that field. So that's why prefixed instructions were introduced. The other thing that we can do is with this field at the end, the comma 0 on the end here, there is a provision for PC relative addressing. So you can put a 1 there, you put R0, and then you put the offset from the address difference between the operand and the address of the instruction. So you get a PC relative addressing mode. Anyway, so the point is that we've got these 2 words and they come in through the iCache kind of one after the other. Now, what the iCache does in pre-decoding is it just takes the first word, it says, oh, okay, it's prefix. Prefix uses instruction index 2, so I'll put that in. And then the second word gets decoded exactly the same, gets pre-decoded exactly the same, I should say, as it did in the word case. Then when we come to actually execute it, the prefix goes through, comes out of iCache into decode 1. Decode 1 sees it and doesn't issue it downstream to decode 2. It just holds on to it until the next one comes along. The next one comes along and it's this, what actually looks like, that suffix looks like, at this point, that looks exactly the same as this load floating double. But what it does is that because it's had the prefix, it actually increments this 260. It just sets the least significant bit to 1. And so then we index into entry 261 in the decode ROM, and that has got the information for the prefixed load floating double, including, you know, that you should decode the extended displacement field from the prefix and the suffix. Okay, then getting on to execute 1 and execute 2. These are fairly straightforward. We previously just had a single execute stage, but for various reasons we added an extra stage. We do all instructions here except for load, store, and floating point instructions. And actually, as an exception to that, 64-bit integer multiply and integer division we now do in the floating point unit if you have a floating point unit, because the floating point unit is optional. If you don't have a floating point unit, then they're done just by some extra logic in execute 1 and execute 2. But it turns out that the floating point unit has all the machinery for doing both those multiply and divide instructions, and it can in particular do integer division more quickly than we were doing previously, which was just a kind of shift register bit at a time type thing. So we have these submodules that handle these different sorts of instructions. A main adder, as you might expect, that does all the different variants of add, subtract instructions and a few other things as well. We do exception detection and interrupt generation here. So this is where we decide when we need to take an interrupt. We have interlocks to make sure that we don't complete out of order. So decode 2 was ensuring that we didn't dispatch instructions until we had the operands for them. This is ensuring that, let's suppose you had the divide and then you had the add, but they didn't depend on each other, and the divide takes a long time and the add is quick. The add gets stalled in execute 1 until the divide is ready to complete. And so then the divide completes and then the add completes after that. That makes sure that we write our values back in order, which helps us to handle various hazards right after right hazards correctly. Now, most integer computations just take 1 cycle and their results can be forwarded to decode 2. So then you don't get a bubble from a dependency. But there are some instructions, the count leading 0, count trailing 0 instructions, the population count instruction, 32-bit multiply, and some move from special purpose register instructions actually take 2 cycles. So then they go, the result appears in execute 2 and then gets written back. Execute 2 updates special purpose registers, does condition code result generation for dot form instructions. That's talking about in the power instruction set, you can have like an add instruction will just compute the value and write the value back to a register. But if you put a dot on the end, so it's add dot, a period, that does the add, writes the result to the register, and also updates condition codes. And so that's where the result gets tested to see was it less than, equal, or greater than 0, and that kind of thing. Now, load store 1 and 2 and decache, these work tightly together. So load store 1 gets its instruction from execute 1. Now, one of the things that it has to handle is misaligned accesses. So in the Power ISA, misaligned accesses are permitted and generally speaking not permitted to cause an interrupt or a trap just because of the misalignment. I mean, there are exceptions to that rule, but most loads and stores, you can specify any address you like. So it could be an 8-byte double word load, but the address in hexadecimal could end in a 7, and you're supposed to be able to handle that. So in that case, what we have to do is we actually have to do 2 requests to the data cache, because the data cache only handles 8-byte aligned accesses. So in that case, load store has got a state machine that does the first one, does the second, let's say it's a load, it sends the first one to the data cache, gets the value back and remembers that, then asks for the next double word, gets that back, and then it stitches the 2 results together in the right form and sends that off to completion. The other thing it does is that for the load floating single precision and store floating single precision instructions, because data is always kept in double precision form in the floating point register file, these load and store instructions have to convert to and from single precision. So there's converting from single precision to double precision, and that's mostly fairly straightforward except for denormalized single precision values. And similarly, double precision to single precision is mostly fairly simple, except where the value is in the range of a denormalized single precision value, where you have to generate the denormalized value. Now, the data cache has got both the cache tags and the TLB, and this is virtually indexed. This is a virtually indexed cache, and we do the trick of looking up both the cache tags and the TLB in the same cycle, and then doing comparisons of the result from the TLB and the result from the cache tag to see where we find that we've actually got a match. So that's all done in the second cycle, and then we know which way of the cache, because it can be a multi-way cache, then to select and to supply back to load store 1 and load store 2 actually, and back, and eventually to write back. So we have a load to use latency of, I think, 2 cycles, and we've put in a fair bit of effort to make that as small as possible, and that has actually introduced a certain amount of complexity there, because we're trying to cram it all down into just the 2 cycles, rather than having a longer load to use latency, because that would make it perform less well. Now, attached to the data cache and the instruction cache, we have a memory management unit which is able to do address translation, so that we can run Linux. So we have virtual addresses that get translated to physical addresses. In the ISA, there are actually 2 ways that this can be done. Either using a hashed page table, which is what the power instruction set traditionally had from the beginning, power 2 days up until actually power 9. And so that's used by all of the older software, AIX, IBM I, older Linux kernels all expect that hash page table. MicroWatt doesn't implement that. There's now also a radix page table, which was introduced basically because with Linux running on power, we had that the core kernel code was using a radix tree, but the hardware was using a hash page table, so we were spending time basically translating between these 2 different things. With the radix page table, it was designed specifically so that Linux kernels could use it directly, and that the page table that is accessed by the core memory management code in Linux could be exactly the same table that is accessed by the hardware. So that's what we implement, because I'm much more interested in running Linux than anything else. So the ISA defines a very general tree structure where you have a partition table, a process table, and then radix page tables of effectively any number of levels, although in practice, it's 4 levels. So it defines this very general structure, but there are basically 2 standard layouts defined in the ISA. MicroWatt actually implements the full generality, because it just uses a state machine to walk through these radix trees, and it's relatively easy just to make that use the information in the tables that's there in order to define the format. So MicroWatt doesn't rely on having one of these 2 standard layouts. It just walks through what's there. So we can have an address space size up to 62 bits. I don't know why you'd need that big of an address space size when you could, you've only got probably a gigabyte of memory. But anyway, it has this full generality. Then we have level 1 TLBs. These are fairly simple. The MMU is a state machine. It's not particularly fast. There's no kind of level 2 TLB at this stage, although I do want to do that. And we don't currently implement the 2-level translation that is in the ISA for supporting virtual machines. So in the ISA, there's the capability that you can have, let's say, Linux running in a virtual machine, in a partition, and that can have its own tables that specify a translation from its effective address to to a partition kind of logical address. And then the hypervisor can specify with another set of page tables, it can specify the translation from that partition logical address to the actual physical address. And we don't implement that at the moment, although that would be a cool thing to try and do. Okay, just quickly on the floating point unit. As I said, it's non-pipelined. Its control is a state machine, and the intention in implementing it was really to do something that could be hopefully regarded as a reference implementation that handles all of the architected conditions and all of the things that the architecture says you have to do, that it would do all of those things in hardware. So it handles denormalized operands, it handles results that need to be denormalized and does that. It handles all the underflow and overflow conditions that are defined in the architecture, including the trap-enabled and trap-disabled results. So in the architecture, there's provision that if you don't have, let's say, an overflow interrupt enabled, so you don't want to worry about getting overflows. What it will do then is that if a value overflows, it will just produce an infinity value. Whereas if you do have overflow interrupts enabled, that's called the trap enabled case, what it does is it, in order not to lose information, it produces the result, but then it adds an offset onto the exponent because the exponent is too big to store in the exponent field of the result. But what it does is it subtracts a certain amount and then gives you that result, but gives you an interrupt. So the idea then is that an interrupt and a trap handler, if it gets control after that, is able to look at the result and say, oh, I know what the result should have been. Whereas in the trap disabled case, because you've substituted an infinity, you've lost all the information about what exactly the answer should have been. So I've got a diagram here of the floating point unit. This is a simplified version of the data paths. We have the operands coming in here and going into these A, B, and C registers. We then have an adder, which is a 64-bit adder, and we have a multiply add unit, which can multiply two 64-bit numbers together and add on a 128-bit add end and produce a 128-bit result. And that we implement typically using, if there's DSP type resources, often in FPGAs, you've got blocks that are called DSP blocks that have multipliers and adders and that kind of thing. And so particularly on Xilinx FPGAs, this is implemented with those. And I think actually on Lattice ones as well. Then we have R down here is our result register. And then we have S, P, and Y. S is an extension to the R that stores less significant bits. The P and the Y are 64-bit registers that store values that are used in things like divide and square root, where we're using iteration with Newton Raphson and doing multiply, add type operations, iterating on those to get, well, in the case of divide, it's a reciprocal estimate that gets refined. And in the case of square root, it's the Newton Raphson square root. There's an iteration that you do, and each iteration gives you more bits of the result. So that's what they're used for. And then we have a count zeros that's used for normalizing, a shifter that can shift plus or minus 56 bits or so in one cycle. So R and S together can be shifted left or right and put back into R. And then eventually you end up with the result in R, and that goes to right back. So that's a quick spin through the MicroWatt core. Do we have time for questions? If not, if there's
Any
no
questions from the participant side?
Well, if not, then thank you all for listening.
Okay, there are no questions. Once again, I thanks to our honorable speaker.
Hello, sir.
Yeah.
Can you hear me?
Yes.
Yes, I can hear you.
Thank you, Dr. Paul. In this execute 1 and execute 2, are we dividing the sub operations of the floating point in the execution 1, then sending it to execute 2 as the remaining operations of the floating point unit?
So floating point instructions don't actually really go into execute 1. I mean, I know I said that. That's the way the code is currently structured. It's a little bit misleading because really they effectively go straight from decode 2 into the floating point unit, and then there's just some logic in execute 1 to make sure that we stall and don't complete out of order. But there's nothing actually done with the floating point instruction in execute 1. And the same with load store. That they're really going straight from decode 2 down into load store, and the kind of apparent path through execute 1 is just an artifact of the way that the code is structured. Does that make sense?
Yes, sir. Yeah. Thank you.
Any other questions? No questions. Okay. So if there are no questions, once again, I thanks to our honorable speaker, Dr. Paul Mackerras. Your expertise, insights, and thought-provoking presentations have not only enlightened us, but also sparked meaningful conversations and ideas that we will carry forward. Thank you for your time, your dedication, and for making this gathering a memorable one. We are immensely grateful for your presence and your contributions. Thank you very much, sir.
Thank
I
you.
hope that all the participants are benefited from the session. I thanks to all the participants for joining the session. Thank you all.